Today's lesson focuses on sound waves. Now, we've been talking about waves for quite a while, but today we're going to focus on how sound travels and exactly what it means for frequency and amplitude with dealing with sound. So we can describe sound waves as being mechanical because they need particles in which to transfer their energy. They're longitudinal because the energy travels in the same direction as the sound or the particles are moving. And it's pressure waves because as the energy is transferred from one particle to the other, it causes them to squeeze together and become more pressurized and then relax and separate to become depressurized. Now, the sound is produced by this back and forth motion of the particles. They're vibrating back and forth, and so as one of them starts to vibrate, as I start to speak, one little particle vibrates, and the next one over catches its energy or is touched by the first particle and it absorbs its energy and it keeps on transferring back and forth. And so we have this back and forth motion, and it's a domino effect because from one simple little vibration of one particle, it will spread throughout all of them, just the way gases do fill up the room. Well, sound travels in the same direction. Now we have the wavelength of sound waves are looked at with a full compression where it's squeezed together in the really tight areas, and a refraction where it's relaxed as the energy moves along. So we usually equate this to the sinodal waves of the up and the down motion that you see in a sound detector. Now, it's not the same as transverse waves, but we use this idea to help us understand the sound waves because it's easier to see it this way than try to see how close together the particles are being squeezed. So we have pressure on the y-axis and time on the x-axis. And so we have the wavelength, like I said, a relaxed area plus a compressed area equals a full wavelength. Now, the period is usually what we use in order to calculate frequency because it's easier for us to see the separation between the height and the low instead of trying to see the complete one. We're looking at just this little section. And so period is usually what we measure, and then from there we can actually calculate the frequency because it's the reciprocal 1/T. It's still measured in hertz, but now frequency, when we're talking about sound, is dealing with what we call pitch. It's the high frequency is a high pitch like a flute, a violin. We have low frequencies or smaller numbers, which low pitches such as a bass guitar or a tuba. Human hearing allows us to really focus between 20 hertz and 20,000 hertz. It's a big range. Dogs, though, on the other hand, go from 50 hertz, so it's not as sensitive, but they can go all the way to 45,000 hertz. And elephants are on the lower range of 5 hertz all the way up to 10,000 hertz. So their hearing is not as sensitive in the higher range, but it definitely is better on the lower range. We also have amplitude, which in sound is measured in terms of intensity, and intensity is calculated by the energy being pushed through the medium divided by the time plus the area. And so time meaning as it's moving along, it's taking longer to move around, it's spreading out throughout all the area available, and so the energy starts to seem like it is getting decreased, but since it's being spread over and shared amongst all these particles, really it's still the same amount of energy because we can't create or destroy it, it's just spread out to more region. Now, intensity in terms of human hearing, we measure it in what we call the scale of decibels, or lowercase d with a capital B as its symbol. Human threshold of hearing starts at 0 decibels, which really isn't really zero. This scale is measured in the powers of 10. So at 10 to the 0, which is really 1, or 0 decibels, we have the threshold of hearing. In other words, it's the most minimal amount of sound that you can hear, like a pin dropping, safety pin dropping, those very, very light tones. Now we have normal conversation hearing is at 10 to the 3rd power, or 30 decibels. So that's normal conversations that we have with most people. Up in the higher ranges, like if you go to a rock concert and your ears eventually start hurting you, that's because you're getting to the higher range that really will start causing us problems, which is 10 to the 11th power, or 110 decibels. And then we have 10 to the 16 decibels, which comes out to 160 decibels, or sorry, 10 to the 16 power, or 160 decibels, gives you instant perforation of the human eardrum. In other words, the energy is so intense, it punctures or breaks your eardrum, which is what receives the sound. And later on, we will be talking exactly on how the ear perceives and how it can catch these energy powers going through, and how we eventually transfer it into what we hear or sound. Now, another issue between hearing loudness also has to do with a mixture of what frequency it's in and the energy level. Because some sounds, the higher the range you go, it seems like it's a louder sound, but really the intensity may be the same. It's just that with these two in combination, it makes it sound louder, and it does cause us some problems. The donk whistle is way higher than what we can hear. It's at a 25,000 hertz, and so no, that's beyond our capability of being able to feel those vibrations that are caused. So this is a really quick overview of our sound waves. And again, we can go back to the speed of sound, which is calculated by frequency times wavelength. So yes, we would need to know frequency in hertz, we would need to know the wavelength in meters, and we can calculate the speed of sound. And we're going to get into more details of what things affect the speed of sound, because if we're talking about particles moving, we have to look at the states of matter, which in turn is temperature related, and we'll look into more detail about those things. But do recall that we can calculate just basic speed of sound by looking at the frequency times the wavelength, and our unit for that would still be meters per second.